Every human has asked this question at some point. Why are we built this way? Why do we age, lose our memory, feel anxiety, struggle to sleep, give birth in pain, or live with bodies that seem full of flaws? The answer isn't bad design, it's evolution. These are 14 ways evolution never quite finished the job. Picture two people living tens of thousands of years ago. Let's call them Chill Bob and Anxious Alice. Bob is relaxed, always has been, heart rate low, vibes immaculate. One afternoon there's a rustle in the grass nearby. Bob glances over and thinks, probably wind, and goes back to lunch. Alice hears the exact same rustle, and her brain just loses it. Heart rate spikes, adrenaline floods in. She's up a tree before she's even consciously decided to move. Now here's the question that actually matters. Who's right more often? Bob is. Almost every single time it really is just the wind. 99 times out of 100, Alice looks a little ridiculous, sitting in a tree, hyperventilating over a breeze. But what happens on day 100 when the rustle actually is something that wants to eat her? Bob doesn't get a second chance. Alice does. And that's really the whole story of why anxiety still exists. We're not really the descendants of the chill ones. Evolution isn't graded on being right most of the time. It's graded on not being wrong on the one day it counts. So the anxious, jumpy, easily startled version of the human brain is the one that got passed down. Every generation, over and over, until it became us. Okay, but why does it feel so bad though? Fair question. If anxiety is so useful, why does it feel like garbage? This is where evolutionary psychiatrist Randolph Nesser comes in. He's basically the guy who took "why does anxiety exist" seriously as a scientific question instead of just a medical complaint. And he came up with something called the smoke detector principle. And once you hear it, you cannot unsee it everywhere. Think about the smoke detector in your kitchen. Burn a piece of toast, it screams at you. 99% of the time, there's no fire. Just you, waving a dish towel at the ceiling, muttering at an inanimate object. Is the detector broken? No, it's designed that way on purpose. A false alarm costs you 30 annoyed seconds. A missed real fire costs you your house. So the engineers didn't build a detector that's usually right. They built one that almost never misses, even if that means it's wrong constantly. Nessie's argument is that your nervous system runs on the same math. When the cost of a false alarm is small, a little discomfort, a wasted worry, but the cost of missing a real threat is catastrophic. Natural selection doesn't build a brain that's usually calm and occasionally right. It builds a brain that overreacts constantly because overreacting is cheap and underreacting is fatal. So, yeah, your anxiety is a smoke detector. And it's doing its job by going off over burnt toast because every so often it's a real fire. Anxiety isn't just a feeling, it's a full physical shutdown and reroute of your entire body. And almost none of it is random. Ever notice your stomach drops when you're anxious? Digestion is expensive energy-wise, so the second your brain thinks there's danger, it pulls blood away from your gut and sends it to your muscles. Because digesting a sandwich is a very low priority when you might need to run. Chest feel tight, breathing shallow and fast. That's your body opening your airways for more oxygen while tensing your torso, basically bracing for impact. Cold, clammy hands. Your body's pre-cooling itself because it's assuming you're about to sprint, and sprinting generates heat. None of that is malfunction. That's a coordinated full-body response. And it's driven by the HPA axis, the hypothalamic pituitary adrenal axis, which is basically the chemical chain of command your brain uses to say, prepare for danger, and mean it. Okay, so if the system works this well, why are we in the middle of what genuinely looks like a modern anxiety epidemic? Here's the mismatch. In the ancestral world, danger was acute. You ran from the leopard for 5 minutes and then it was over. You either escaped or you didn't, and either way your body got the signal to stand down. Stress hormones cleared out, baseline restored. Modern stress doesn't work like that. It doesn't resolve in 5 minutes. It's a slow drip. Notifications, deadlines, the vague dread of your group chat going quiet after you sense something a little too honest. Recent research on what's being called evolutionary mismatch, including a 2026 review connecting modern chronic anxiety to what researchers are calling a kind of polycrisis of accelerating social and technological change, makes the case that a lot of our defense systems just weren't built for stress that never fully switches off. Related work on the HPA axis backs this up. When the threat never resolves, cortisol doesn't get the signal to clear out either. It just lingers. And cortisol that lingers for months isn't neutral. It wears on the immune system and, over time, is associated with measurable changes in brain regions tied to memory. It's like flooring your car in first gear for 100 miles straight. The engine wasn't built to redline that long. Eventually something's going to overheat. So here's a thought experiment. If anxiety is this costly, this exhausting, could we just edit it out? Wouldn't life be better without it? Turns out we don't have to imagine the answer. There's a real, extremely rare condition called Urbach-Wieder disease, which, in some cases, slowly calcifies and destroys the amygdala, the brain's fear processing center. The most studied case is a woman researchers refer to only as patient SM. And her story is genuinely unsettling in the best possible scientific way. In lab studies, she handled snakes and spiders that most people recoil from, and described it as curiosity, not fear. In real life, she was once held up at a robbery. She reported no fear during the encounter, and she went back to the same location the next day. Sounds kind of incredible, right? Fearless. No anxiety weighing her down. Except it isn't a superpower. It's a vulnerability. Without that internal alarm system, she and other patients with similar amygdala damage have shown real, documented difficulty picking up on threat cues other people register instantly. The kind of subtle social and situational red flags that keep most of us out of trouble without us even noticing we're using them. Turns out the smoke detector isn't the problem. The world without one is. You don't have to declare war on your anxiety. You don't even have to like it. You just have to recognize what it's actually doing, and maybe give it slightly less credit as a threat forecaster and slightly more credit as a very old, very loyal, slightly overzealous smoke detector. It's not trying to ruin your day. It's trying to make sure you have a tomorrow. But anxiety isn't the only thing evolution left unfinished. Tonight, you'll go to bed without thinking much about it. You'll find a comfortable position, close your eyes, and expect sleep to come naturally. If it doesn't, you'll probably blame the mattress, or the pillow, or the temperature. Comfort has become something we barely notice until it's gone. Now imagine someone carrying you back 70,000 years. Nothing about your body changes. You're still you. The only difference is where you wake up. There are no houses waiting for you. No bedroom, no bed, just a small camp surrounded by darkness. The ground beneath you is uneven. The air smells of smoke. Somewhere beyond the fire, something moves. Could you actually fall asleep? Most people think the answer is obvious. Our ancestors did it every night. Surely we'd manage too, but that's where the story becomes strange. Because when archaeologists began looking for the oldest places humans slept, they didn't find people lying directly on cave floors. They found something far more familiar, a bed. Not the kind you're imagining. There was no wood frame, no mattress. But there was intention. In a cave called Sibudu, on the eastern coast of South Africa, archaeologists uncovered layers of compressed grass, dating back roughly 77,000 years. At first, it looked like ordinary plant material, until they noticed the pattern. The grass had been gathered, carried into the cave, spread into flat layers, then covered with fresh material again. This wasn't debris. Someone had built a place to sleep. Then someone else rebuilt it, again and again. Generation after generation, it pushed the oldest known evidence of human bedding back tens of thousands of years. That discovery changed something important. Humans weren't simply adapting to the ground, they were already changing it. Which raises another question. If prehistoric people were making beds, how uncomfortable was the ground in the first place? The answer may have had less to do with rocks, and more to do with what was living beneath them. When researchers looked closer at those ancient beds, they found leaves mixed into the grass. Not just any leaves. They came from Cryptocarya woodii, a tree whose leaves contain compounds that repel insects. Today, people still recognize those properties. 77,000 years ago, nobody knew anything about chemistry. Yet those same leaves appear repeatedly in different layers of bedding. That probably wasn't an accident. Somebody had learned that sleeping on certain plants meant fewer bites, fewer parasites, a better night's sleep. Nobody knows how they discovered it. Maybe they noticed children slept more peacefully. Maybe one family happened to use different plants than another. Or maybe it took hundreds of generations of trial and error before anyone realized certain leaves made the night a little easier. Whatever happened, the knowledge survived. Long enough for archaeologists to discover it tens of thousands of years later. Then they found something even stranger. Every so often, the entire bedding layer had been burned, not once, repeatedly. The first thought was obvious. Perhaps a fire had gotten out of control, but the pattern kept repeating. Fresh bedding, weeks or months of use, then fire, then new bedding. Researchers now think those ancient people were deliberately burning their sleeping mats before replacing them. Why would they do that? Because grass doesn't just collect dirt, it collects fleas, ticks, mites, parasites that multiply surprisingly quickly once people sleep in the same place night after night. Burning the bedding would have destroyed them before they spread. Without realizing it, those people may have been practicing one of humanity's earliest forms of hygiene. That's an odd thought. When most of us picture prehistoric life, we imagine chaos. People surviving one day at a time. Little planning, little organization. The archaeology paints a different picture. Sleeping areas, working areas, fireplaces, spaces that were used for different purposes, sometimes for thousands of years. The camp wasn't random. It was organized, which creates another mystery. If humans had already figured out how to make comfortable beds, what were they really afraid of once the sun went down? Because discomfort wasn't the biggest danger. Night was. A human being doesn't see particularly well in darkness. We don't hear like wolves. We don't smell like bears. Compared to many predators, we're remarkably vulnerable after sunset. On paper, we should have been one of the easiest animals to hunt, so why weren't we? For a long time, researchers assumed the answer was caves. People hid inside them until morning. Simple. Except caves come with a problem. Humans aren't the only animals that like caves. Lions use them. Leopards use them. Hyenas use them. Sometimes bears do too. A cave could protect you, or it could become the last place you ever slept. Then archaeologists noticed another pattern. Almost everywhere they found long-term human camps. They found evidence of repeated fires, not occasional fires, daily fires. Fires that burned in the same places over and over again. Fire gave people warmth. It let them cook food. It extended the day after sunset. But it may have done something even more important. It changed the balance between humans and everything watching from the darkness. Because if there was one thing even the largest predators treated with caution, it was fire. And that may have been the reason humans could finally do something that had once seemed impossible. Close their eyes and sleep. But fire only solved one problem. It didn't explain how humans actually slept. Think about it. A fire burns for hours, then it dies. The forest doesn't. Every sound is still there, branches breaking, animals moving, the wind changing direction. If a leopard walked into camp at 3 a.m, would everyone really stay asleep? For decades, anthropologists wondered the same thing. Maybe ancient humans didn't sleep the way we do. Maybe nobody ever expected 8 uninterrupted hours. That idea became known as the sentinel hypothesis. The idea is surprisingly simple. Imagine 20 people sleeping around a fire. Nobody is assigned to stay awake. Nobody is standing guard. Instead, people naturally drift in and out of sleep at different times. One person wakes to add wood to the fire. Another wakes because they heard something. Someone else wakes to check on a crying child. For a few minutes, someone is always awake. Then they fall asleep, while someone else wakes. No schedule, no planning, just dozens of human sleep cycles overlapping. In 2017, researchers studying the Hadza of Tanzania, one of the world's last hunter-gatherer societies, noticed something remarkable. Across hundreds of hours of observation, there were only a handful of minutes during the entire night when every adult was asleep at exactly the same time. Almost every moment, someone was awake. Sometimes only for a minute, sometimes much longer. The camp never became completely unconscious, not because anyone was forced to keep watch, because human sleep naturally staggered itself. It's an elegant idea, and it would have made prehistoric camps much safer. But even that isn't the whole story, because another mystery remained. If humans evolved sleeping outdoors, why are we so bad at it now? Go camping for the first time, and many people barely sleep. Every noise feels important. A squirrel sounds like a bear. A branch snapping feels close enough to touch. Most people blame modern life. We've become too comfortable, too dependent on mattresses, but sleep researchers think something else may be happening. Your brain isn't malfunctioning. It's doing exactly what it evolved to do. Studies have shown that when people sleep somewhere unfamiliar, one side of the brain often remains more alert than the other. Scientists call it the first night effect. Even in a modern laboratory, your brain doesn't fully relax in a new environment. Part of it keeps listening, almost as if it's standing guard. Nobody knows exactly why this happens, but it's easy to imagine why that ability would have helped thousands of years ago. A strange place, unknown sounds, unknown predators. The people who stayed slightly more alert may have survived more often than the people who slept too deeply, which means your terrible first night in a hotel or a tent might actually be ancient survival instincts refusing to switch off. Then, another discovery complicated everything again. Humans don't actually sleep very much. Compared to other primates, we sleep surprisingly little. Chimpanzees often sleep close to 10 hours. Some monkeys sleep even longer. Humans average around 7. At first, that seems like a disadvantage. Less sleep should mean less recovery, less energy, less survival. Instead, the opposite happened. Researchers found that although humans sleep fewer hours, a larger percentage of our sleep is spent in deep sleep and REM sleep. The stage is most strongly linked to memory, learning, and emotional processing. In other words, evolution didn't make us sleep longer. It made our sleep more efficient, which raises one final question. If prehistoric humans had beds, used insect-repelling plants, cleaned their sleeping areas, slept around protective fires, and naturally staggered their sleep throughout the night, were they really sleeping under worse conditions than we are? Or have we been imagining prehistoric life completely wrong? For generations, movies showed exhausted cave people collapsing onto cold rocks. The archaeology tells another story. People collected soft grasses, replaced them regularly, selected specific plants, organized living spaces, protected themselves with fire. They weren't simply surviving each night, they were engineering better sleep. Long before cities, long before farming, long before anyone understood what bacteria, parasites, or sleep cycles even were. Perhaps that's the strangest part of all. We often think civilization taught humans how to sleep comfortably. The evidence suggests we started solving that problem tens of thousands of years before civilization even existed. Your mattress is newer, your pillow is newer, your bedroom is newer. But the idea of making tomorrow night's sleep better than last night's may be almost as old as humanity itself. And maybe that's why the real question was never, why can't humans sleep anywhere? It's why we keep imagining that our ancestors did. Because when archaeologists finally uncovered the places where they slept, they didn't find people accepting discomfort. They found people doing exactly what you'd probably do tonight, looking for the best place to close their eyes. And sleep isn't the only strange compromise our bodies make. Imagine waking up tomorrow morning with a biological superpower, perfect, flawless memory. From that moment on, your brain acts like a 4K video camera with an infinite hard drive. You read a 500-page book once, and you can recite it backward. You never forget a name, a face, or a password. You can perfectly recall the exact temperature of the air, the smell of the room, and the exact words spoken during a conversation you had on a random Tuesday 10 years ago. It sounds like the ultimate evolutionary advantage. If survival is based on learning from your environment, then a creature with a perfect memory should be the ultimate survivor. It would never make the same mistake twice. It would map every predator, every food source, and every danger with absolute terrifying precision. So, why didn't natural selection build us this way? If evolution can engineer a brain that processes billions of calculations a second, why did it give us a memory system that constantly glitches, forgets where we put our car keys, and completely erases 99% of our daily lives? For a long time, science assumed that forgetting was just a mechanical failure. We thought memories were like photographs left out in the sun. Over time, they just passively faded, degraded, and rusted away. We viewed forgetting as a weakness, a flaw in the biological hardware. But modern neurobiology has completely shattered that assumption. The absolute cutting edge of memory research has proven that forgetting is not a passive accident. It is an active, aggressive, and highly energy-intensive software program. Your brain is not failing to remember. It is deliberately, forcefully deleting your files, and it is doing it to save your life. To understand why perfect memory is a death sentence, we have to look at how computer scientists train artificial intelligence. When you build a machine learning model, you feed it massive amounts of data. But AI developers face a massive, constant problem called overfitting. If an AI is allowed to memorize its training data too perfectly, it becomes incredibly rigid. It learns the specific data so flawlessly that it completely loses the ability to adapt to anything new. Imagine you are programming an AI robot to survive in the prehistoric African savanna, and you train it to avoid lions. The robot gets attacked by a lion under a massive baobab tree at 3 p.m. while it is raining, and a specific flock of red birds is flying overhead. If the robot has a perfect memory, it memorizes every single pixel of that event. But because its memory is so highly specific, it creates a fatal flaw. The robot learns that danger only looks exactly like that. The next day, if a lion attacks at 10 a.m. under a different tree with no birds around, the robot's perfect memory cross-references the files, sees that the details don't match, assumes it is perfectly safe, and gets eaten. For the robot to survive, you have to introduce noise into its code. You have to force it to delete the irrelevant details, the birds, the rain, the specific tree, so it can extract the underlying rule. Large cats with sharp teeth are dangerous. The human brain solved the overfitting problem millions of years ago. Evolution realized that a perfect memory of the past is completely useless because the past never repeats itself exactly. The world is chaotic, dynamic, and constantly changing. If you remember every single detail of a traumatic event perfectly, your brain becomes paralyzed by specifics. You lose the ability to generalize. Forgetting is not a memory glitch, it is the biological mechanism of wisdom. By aggressively scrubbing away the useless, hyper-specific details of your day, your brain extracts the generalized rules of survival. You forget the exact color of the snake, but you remember that long, slithering things in the grass are a threat. But how does your brain actually hit the delete button? In the last few years, neuroscientists have discovered the exact biological mechanisms of active forgetting, and it is completely mind-blowing. When you learn something new, your brain doesn't just store it in a magical cloud. It physically builds a new structure. A cluster of neurons wires together into a physical web called an engram. As long as that engram stays connected, the memory exists. But your brain employs specialized immune cells called microglia. You can think of microglia as heavily armed microscopic gardeners. While you are sleeping, these microglia crawl through your brain tissue, actively inspecting your engrams. When they find memories that are too specific or information that hasn't been used recently, they literally eat the connections. They physically sever the synapses, breaking the web and dissolving the memory forever, freeing up the biological hardware to be used for something else. And the brain's commitment to deleting the past gets even more extreme. Deep inside your brain is a seahorse-shaped structure called the hippocampus. This is your memory control center. For decades, scientists believed that humans were born with all the brain cells they would ever have. But we now know that the adult hippocampus constantly generates brand new neurons, a process called neurogenesis. You would think that adding new brain cells would make your memory better, giving you more storage space. But recent studies have proven the exact opposite. As these brand new neurons grow and integrate into the hippocampus, they aggressively disrupt and overwrite the older neural circuits. The very act of growing new brain cells causes you to forget the past. Your brain is intentionally bulldozing its old neighborhoods to build new ones. It is sacrificing the past to ensure that you are perfectly optimized to learn and adapt to the future. If you want proof of how devastating it would be if this deletion software broke, we just have to look at a very real, highly documented medical condition called highly superior autobiographical memory, or HSAM. There are a few dozen people on Earth whose brains possess a genetic anomaly that prevents them from actively forgetting. They have the superpower of perfect memory. They can tell you exactly what they were wearing, what they ate, and what the weather was on any random date 20 years ago. But it is not a superpower. For almost all of them, it is a debilitating curse. Because their microglia do not prune their engrams, their minds are chaotic, deafeningly loud, and endlessly cluttered. They are constantly bombarded by hyper-vivid flashbacks, triggered by the slightest sights or smells. Imagine trying to focus on a conversation today, but your brain is simultaneously playing an unpausable 4K video of a fight you had with a friend in 2011, complete with the exact raw emotional pain you felt in that exact second. People with HSAM struggle to adapt to new environments. They struggle to forgive, and they are heavily prone to severe anxiety and depression. They are biologically trapped in the past, completely overwhelmed by the crushing weight of their own data. So the next time you beat yourself up for forgetting a name, losing your train of thought, or not being able to remember what you had for lunch 3 days ago, you need to reframe exactly what your biology is doing. you do not have a bad memory. Your brain is not failing, and your hardware is not breaking down. You are experiencing a highly advanced evolutionary filtration system working at absolute perfection. Your brain is actively clearing away the clutter, deleting the noise, and destroying the irrelevant details to ensure your mind stays flexible, adaptable, and sharp. Evolution didn't give you a perfect memory, because evolution wanted you to survive. And in a constantly changing universe, the ability to forget is the ultimate biological superpower. Our brains weren't the only thing evolution chose not to perfect. Every single mammal on Earth lives outdoors, and almost every single one relies on a thick coat of fur to survive. Fur is nature's ultimate multi-tool. It insulates against freezing night temperatures, blocks razor-sharp brush, and shields delicate skin from blistering ultraviolet radiation. Except for us. Humans are a bizarre, pathetically naked anomaly. We are the only primates who stripped off our built-in protection. Losing our hair forced our ancestors to spend thousands of generations inventing clothes, building artificial shelters, and freezing in the elements, which raises a massive evolutionary contradiction. Why would natural selection deliberately strip away our most vital survival barrier, leaving us entirely exposed? To understand how bizarre we are, we have to look at the sheer engineering genius of animal fur. Fur isn't just a layer of hair, it is a dynamic climate control system. In the bitter cold, tiny muscles attached to each hair follicle contract, pulling the fur upright to trap a thick layer of dead air right next to the skin. This layer of trapped air acts as a highly efficient thermal blanket, reflecting body heat backward and keeping the animal warm in sub-zero blizzards. In the scorching heat, that exact same layer of fur acts as a shield, blocking the ambient heat of the outside environment and the direct radiation of the sun from reaching the delicate flesh underneath. Fur prevents external moisture from chilling the skin, deflects the physical damage of thorns and rocks, and acts as a barrier against deadly insects. Yet, millions of years ago, on the dangerous African savanna, our ancestors chose a path of absolute vulnerability. They systematically turned off the genetic pathways required to grow thick body hair, leaving themselves completely bare. From a traditional survival standpoint, this looks like absolute biological madness. A naked primate is a fragile primate. Without fur, our skin is highly susceptible to sunburns, infections, deep cuts, and hypothermia. If an early human was forced to spend the night exposed to a sudden drop in temperature, their metabolic engine had to work twice as hard just to keep their internal organs functioning. Every piece of evolutionary logic dictates that natural selection should have aggressively eliminated hairless primates from the gene pool within a single generation. For decades, science has split into two major camps to solve this mystery: the parasite theory versus the radiator theory. The first major attempt to explain this paradox centers on the hidden dangers of the prehistoric wilderness. Thick, dense fur is a magnificent habitat for blood-sucking parasites. For millions of years, early hominids lived in communal nests and caves, creating the perfect breeding ground for biting lice, ticks, fleas, and mites. These parasites weren't just an annoyance, they were highly lethal vectors for catastrophic diseases and plagues. A primate covered in dense fur was constantly hosting an entire ecosystem of biological threats that actively drained their energy, compromised their immune system, and introduced deadly pathogens into their bloodstream. According to the parasite theory, going completely bald gave our ancestors a staggering survival advantage. It turned our skin into a hostile, unlivable desert for biting insects. Without the cover of fur, ticks and lice had nowhere to hide, allowing early humans to easily spot and pick them off their bodies. Furthermore, clean, hairless skin quickly became a powerful visual signal within the tribe. It broadcasted a loud message to potential mates. My skin is free of disease, my immune system is strong, and I am biologically fit. But as compelling as the parasite model sounds, it hits a massive, undeniable roadblock. While going hairless reduces the threat of ticks, it introduces the lethal threat of exposure. Prehistoric nights on the African savanna were bitterly cold. Long before early humans ever invented clothes, wove blankets, or figured out how to build complex shelters, they had to survive the dark hours of the wilderness. A hairless primate would lose body heat at an alarming rate the moment the sun went down. The energetic cost of shivering all night just to stay alive would wipe out any metabolic savings gained from being tick-free. The parasite theory explains why clean skin is useful, but it fails to justify the sheer, life-threatening cost of freezing to death. The real answer required scientists to stop looking at what we lost and start looking at what we gained. We had to stop viewing hairlessness as a missing feature and start viewing it as an active technological upgrade. When you look beneath the surface of human anatomy, you discover that we didn't actually lose our hair follicles. Humans have roughly the same density of hair follicles on their bodies as a chimpanzee of equal size. The difference is that our hair follicles were structurally reprogrammed to produce microscopic translucent vellus hairs instead of thick, coarse fur. And right alongside this change, our skin underwent a radical mechanical overhaul. We completely re-engineered our internal cooling system. Other primates possess very few eccrine sweat glands. They rely primarily on apocrine glands, which secrete a thick, oily fluid through hair follicles that does very little to cool the body. Humans, however, did something completely unique. We multiplied our eccrine sweat glands by the millions, packing them tightly across every square inch of our bare skin. This created an unprecedented biological radiator. Our skin became a massive, highly responsive liquid cooling grid capable of pumping out liters of water directly onto the surface of the body. As the surrounding air moves over this thin layer of moisture, the water evaporates, drawing metabolic heat out of the bloodstream and dropping the body's internal temperature instantly. To understand why our ancestors needed to turn their bodies into a walking water radiator, you have to look at the brutal physics of prehistoric hunting. Quadrupedal mammals like cheetahs, leopards, lions, and antelopes are absolute masterpieces of explosive power. They possess a massive percentage of fast twitch muscle fibers designed to propel them across the landscape at terrifying speeds. A cheetah can sprint at over 60 miles per hour, and a gazelle can effortlessly leap over obstacles while running at a blistering pace. But this explosive machinery comes with a massive physical limitation. It generates a catastrophic amount of internal metabolic heat. When a fur-covered animal sprints, its muscles act like a massive furnace. Because their bodies are wrapped in a thick insulating coat of fur, that heat has nowhere to go. Quadrupeds cannot sweat effectively over their skin. They can only dump heat by panting. Panting requires the animal to forcefully move air back and forth over its moist tongue and respiratory tract. But an animal cannot pant effectively while it is actively sprinting. The mechanics of running force its lungs to coordinate directly with its stride, meaning it has to choose between breathing efficiently or cooling down. Within minutes of intense exertion, a fur-covered animal's internal organs begin to dangerously cook. If its core temperature hits a critical threshold, its brain short-circuits, resulting in immediate heat stroke and physical collapse. This is where the persistence hunting model completely changes the rules of survival. Early humans were physically weak, slow, and completely incapable of outrunning a prey animal in a short sprint. We couldn't catch a gazelle in a race, and we couldn't outrun a lion to save our lives. But we possessed a secret weapon that no other animal on the planet had, the ability to dump heat while moving. Around 2 million years ago, early humans weaponized their naked skin. They did something completely unprecedented in the animal kingdom. They began hunting in the dead heat of the midday sun. Midday on the African savanna is a biological dead zone. The sun beats down with relentless, suffocating force. Every single apex predator, from lions to leopards, is forced to abandon the hunt, retreat to the deepest shade, and remain completely motionless just to keep their brains from overheating. The prey animals gather in tight groups under trees, trying to minimize their movement to stay alive in the blistering heat, but the naked ape didn't hide in the shade. Armed with millions of active sweat glands and zero fur to trap their heat, early humans stepped out into the blinding noon sun. They would locate a target animal and intentionally trigger it into a sprint. The prey would easily burst ahead, vanishing over the horizon in a matter of seconds. To a casual observer, the hunt looked like an immediate failure, but the humans didn't stop. They didn't need to run fast, they just needed to keep moving at a steady, relentless jog. Because their skin was hairless, the sweat evaporating off their bodies kept their internal temperature locked in a safe, stable zone. They were walking radiators, continuously dumping their engine heat into the air while on the move. Miles away, the fur-covered prey animal would stop, standing in the sun, desperately panting to try and lower its soaring core temperature. But before its brain could cool down, the naked humans would appear over the horizon, walking rhythmically, tracking its footprints. Terrified, the animal would be forced to bolt again, generating another massive spike of internal heat that its fur coat trapped directly against its skin. This cycle repeated hour after hour under the brutal midday sun. Run, stop, pant, repeat. The humans never lost track, and they never stopped moving. They transformed the hunt from a contest of speed into a brutal math problem of thermal dynamics. Eventually, the prey animal reached a point of absolute thermodynamic bankruptcy. Its lungs could no longer move air fast enough to cool its blood. Its muscles became stiff, its eyes rolled back, and it literally collapsed flat onto the dirt from heat stroke, physically paralyzed by its own fur coat. The humans would walk up to the incapacitated animal and finish the hunt without ever having to throw a spear in conflict. Natural selection faced a brutal, uncompromising trade-off on the ancient savanna. Fur was a magnificent layer of protection for a creature that stayed in the shade or only moved at night. It kept our ancestors warm during the freeze and protected them from the environment, but that very same fur coat acted as a hard ceiling on our physical potential. It made it mathematically impossible to engage in long-distance endurance movement during the day without dying of heat stroke. Evolution chose to break the ceiling. It stripped away our built-in armor, left our skin completely exposed to the elements, and forced us to endure the freezing nights. It traded a static, passive coat of hair for a dynamic, high-performance, liquid-cooling engine. This single anatomical sacrifice fundamentally altered the trajectory of our species. It allowed us to conquer the most dangerous hours of the daytime wilderness, turning us from defenseless primates, hiding in the trees, into the most relentless, unstoppable daytime hunters the planet had ever seen. We didn't lose our fur because of a biological mistake or a random genetic glitch. We gave it up to fund a revolutionary lifestyle change. Being a naked ape was the exact price we had to pay to turn our bodies into the ultimate endurance machine, trading our physical protection for the freedom to run the world until we were smart enough to build our own. It wasn't just our appearance that changed. You already know what you're supposed to do. Exercise. Clean your room. Finish that project. Go for a run. Read that book you've been putting off. Nobody has to explain why those things are good for you, and yet millions of people still procrastinate. It's so common that we gave it a name: laziness. For centuries, people have treated laziness like a character flaw, a lack of discipline, a lack of willpower. Some even call it one of humanity's greatest sins. which raises a surprisingly difficult question. If laziness is so harmful, why is it so common? Shouldn't evolution have removed it thousands of years ago? After all, our ancestors lived in one of the harshest environments imaginable. If you refused to hunt, you didn't eat. If you ignored danger, you died. If you stayed in your shelter while everyone else gathered food, your family suffered. That doesn't sound like a world where lazy people survived. It sounds like a world where only the hardest workers lived long enough to have children. So why are our brains still so good at avoiding effort? The question itself might be wrong, because evolution never created an animal whose goal was to work hard. It created an animal whose goal was to survive. Those aren't always the same thing. Imagine you're living 50,000 years ago. You don't know when you'll find food again. You don't know when winter will arrive. Every calorie matters. Every unnecessary movement burns energy you might desperately need tomorrow. Now imagine two hunters. One runs everywhere, climbs every hill, chases every animal he sees. The other thinks first. He chooses the easiest path, the closest water source, the hunt with the highest chance of success. Who survives longer? The answer isn't obvious, because nature rewards efficiency, and efficiency often means doing less. That idea appears again and again throughout nature. Lions sleep nearly 20 hours a day. Leopards spend hours lying in trees. Even crocodiles remain almost perfectly still for incredible lengths of time. They're not being lazy, they're conserving energy. Movement is expensive, especially in the wild. The fewer calories you waste, the more you have when survival actually depends on them. Humans evolved under those same rules. Researchers studying hunter-gatherers have found something interesting. People don't spend every waking hour searching for food. The Hadza of Tanzania, one of the best-studied hunter-gatherer societies on Earth, often spend several hours each day resting, talking, repairing tools, or simply sitting together. That surprised early researchers. Many expected prehistoric life to be endless work. Instead, they found periods of intense activity followed by long periods of recovery. It's almost the opposite of modern life. Work, rest, work again, not constant productivity. So if conserving energy was so important, why do some people seem naturally driven to work constantly? History is full of them. People who can't sit still, who build businesses, lead armies, cross oceans, invent new technologies. Were their brains simply wired differently, or was something else happening? The answer may lie inside a part of your brain that's constantly making tiny calculations without you ever noticing. Every decision has a cost. Walk to the river? Calories. Climb that hill? Calories. Build another shelter? Calories. Your brain is constantly asking one question. Is the reward worth the effort? Researchers call this effort discounting. The harder something feels, the less valuable your brain automatically judges the reward to be. Because your brain evolved to avoid wasting energy. Scientists have even watched this happen inside the brain. Regions involved in motivation become less active as the perceived effort increases. Before you've lifted a finger, your brain has already started negotiating with itself. Could this wait until tomorrow? Is there an easier way? Do I really need to do this now? Sound familiar? That negotiation isn't a modern invention, it's ancient. For almost all of human history, saving energy made perfect sense. Today, food is everywhere. Most people don't hunt, most don't gather, yet the brain still behaves as if calories are incredibly precious. And that creates a problem our ancestors never had, because the world changed much faster than our brains did, which raises an uncomfortable possibility. What if what we call laziness is actually a Stone Age survival instinct living inside a 21st century world? For decades, scientists believed they had found the answer. It became known as the thrifty gene hypothesis. The idea was simple. For almost all of human history, food was unpredictable. Some weeks were successful, others weren't. The people who wasted energy or burned through calories too quickly were more likely to starve. So over thousands of generations, natural selection favored bodies that held onto energy whenever they could. On paper, it made perfect sense. A brain that encouraged rest, a body that stored fat, an instinct to avoid unnecessary effort. Those traits would have been incredibly valuable. Then agriculture arrived, then cities, then supermarkets. Suddenly, the same instincts that once protected us were surrounded by unlimited food. The hypothesis became incredibly popular. There's just one problem. Many scientists no longer think it's the full story, because if humans evolved to conserve every calorie, why are some people naturally so active? Why do some children spend all day running? Why do endurance athletes exist? Why did ancient humans walk enormous distances without stopping? The thrifty gene couldn't explain everything. So researchers started looking somewhere else. Instead of asking, why do humans avoid effort? They asked, when do humans decide effort is worth it? Animals rarely choose the hardest way to get food. If two trees produce the same fruit, birds usually fly to the closer one. If two hunting grounds offer the same reward, wolves usually choose the easier hunt. They're constantly solving an invisible equation. Maximum reward, minimum cost. Humans do exactly the same thing. Without realizing it, your brain is constantly comparing effort against reward. Take the stairs or the elevator. Cook dinner or order delivery. Walk to the store or drive. None of these decisions feel like survival, yet your brain treats them as tiny economic calculations. Researchers even gave this tendency a name: the principle of least effort. It appears almost everywhere. We choose shorter routes, shorter words, simpler solutions. We naturally drift toward whatever achieves the same result with less work. It's one of the oldest patterns in human behavior. Then, neuroscience added another piece. Most people think dopamine is the brain's reward chemical. It isn't. Dopamine is heavily involved in motivation. It helps your brain decide whether something is worth pursuing. The expected reward matters, but so does the expected effort. Increase the effort. Without increasing the reward, and motivation often falls. Increase the reward, and suddenly enormous effort feels worthwhile. That's why someone can procrastinate all day, then spend 6 straight hours playing a difficult video game. The brain isn't avoiding effort itself. It's deciding which effort deserves the investment. Then, another discovery complicated things even further. Hunter-gatherers weren't constantly exhausted. In fact, many anthropologists describe their lifestyle as alternating between bursts of intense activity and long periods of recovery. A successful hunt could feed a group for days. There wasn't always a reason to keep burning calories once the immediate goal had been achieved. Modern life is different. Many jobs reward constant activity, even when that activity produces very little. For almost all of human history, working harder didn't always produce better results. Working smarter often did, which creates another uncomfortable question. If conserving energy helped our ancestors survive, why do we admire people who never stop working? The answer may have very little to do with evolution. For most of human history, your reputation depended on providing value to your group. Modern societies often reward visible effort. Those aren't necessarily ancient instincts, they're cultural values. The two aren't always the same. Then there's another misconception. People often say, humans are naturally lazy, but that's not what the evidence shows. Give people a meaningful challenge, a clear goal, and immediate feedback, and they'll often work unbelievably hard. People have crossed oceans, climbed Everest, run ultramarathons, built civilizations, spent decades solving mathematical problems because the reward became worth the cost. Perhaps that's the biggest misunderstanding of all. Evolution created a brain that's extremely selective about which work is worth doing. And sometimes that ancient system collides with a modern world filled with endless low-effort rewards. A swipe, a notification, another video, another snack. Your brain doesn't know these things didn't exist 50,000 years ago. It only knows they provide rewards for almost no effort at all. Competing against that is incredibly difficult, which means the original question may have been the wrong one. Evolution didn't preserve laziness. It preserved efficiency. A brain that constantly asked, can I get the same result while spending less energy? For hundreds of thousands of years, that question kept people alive. Today, the world has changed. The question hasn't, and that may explain why doing the things that matter most often feels harder than they should, because it made us incredibly good at saving energy whenever possible. And not every behavior that seems like a flaw is one. Every human alive today exists because somewhere in the past, their ancestors had children, generation after generation, for hundreds of thousands of years. That's the engine evolution runs on. The people who passed on their genes shaped the future. The ones who didn't usually disappeared from it, which makes one question incredibly difficult to answer. Why has homosexuality never disappeared? It exists in every part of the world, every culture that's ever been carefully studied, every period of recorded history. It survived empires, religions, wars, mass migrations, and somehow it was already there long before any of them existed. If evolution favors reproduction, why didn't evolution simply remove it? It's a question that has fascinated biologists for decades. Not because nobody has an answer, because every answer seems to create another mystery. The first clue doesn't come from humans, it comes from animals. For a long time, scientists assumed same-sex behavior was something uniquely human. Then people started paying closer attention. Two male penguins built a nest together. Female albatrosses raised chicks as lifelong pairs. Male dolphins formed long-term sexual partnerships. Bonobos used sex to calm conflicts inside their groups. Then the list kept growing. Swans, lions, giraffes, bats, bison, even insects. Researchers have now documented same-sex sexual behavior in hundreds of animal species, with observations reported across many more. Suddenly, the question wasn't, why do humans do this? It became, why does nature keep doing this? Because evolution has had millions of years to remove traits that truly prevent survival. Yet this behavior keeps appearing, again and again and again. Almost as if evolution isn't trying to eliminate it at all. But that creates another problem. Evolution doesn't think. It doesn't make decisions. It doesn't care about fairness. It simply rewards whatever leaves behind more copies of itself. At least, that's how most people imagine it works. Reality is much stranger. Imagine a small group of hunter-gatherers, 30 people, maybe 40. Every adult matters, every hunter matters, every child is surrounded by brothers, sisters, cousins, grandparents, aunts and uncles. Nobody survives alone. A child doesn't belong to only two parents. The entire group helps keep that child alive. Food is shared, protection is shared, knowledge is shared. For almost all of human history, survival wasn't an individual project, it was a group project. And that changes everything. Because evolution doesn't only care about your children. Your brothers carry many of the same genes you do. So do your sisters. Their children carry some of them too. Helping your family survive can still help your own genetic legacy continue. This idea became one of the first major attempts to solve the mystery. Scientists called it kin selection. The basic idea is surprisingly simple. Someone without children of their own might invest more time helping close relatives raise theirs. More food, more protection, more knowledge. Those children become more likely to survive. The shared genes continue into another generation. It's sometimes nicknamed the gay uncle hypothesis. It's clever. It makes the intuitive sense. There's just one problem. The evidence is mixed. Some studies have found support, others haven't. It explains part of the puzzle, not the whole picture, which means the mystery remains. So researchers looked somewhere else. Maybe they were asking the wrong question altogether. Maybe evolution isn't trying to maximize the number of children every single individual has. Maybe it's balancing hundreds of different traits at once. Think about height. Being taller can help in some situations. Being shorter can help in others. Neither completely replaces the other. Human populations end up with variation. The same may be true for many behavioral traits. Some genes come with advantages and disadvantages. Remove one, you accidentally remove the other. That possibility led scientists toward another fascinating idea. What if the same genes associated with homosexuality provide reproductive advantages in people who aren't homosexual? At first, that sounds impossible. Until researchers began looking at families. Some studies suggested that female relatives of gay men had slightly more children than average, not dramatically more, just enough to make scientists pay attention. If those findings are correct, the genes might remain in the population because they increase reproduction somewhere else. Not in everyone, just enough people to keep them around. It's called balancing selection. Nature keeps the package because removing it would also remove something useful. It's an elegant theory, and once again, it isn't proven. Different studies have reached different conclusions. Scientists are still arguing about it today. By now, something strange had happened. Every explanation solved one part of the mystery, while creating another. Then, genetics complicated everything even further. For years, people searched for a single explanation, a single mutation, a single gay gene. Something simple, something evolution could easily switch on or off. That's not what they found. When researchers studied hundreds of thousands of genomes, they discovered something far more complicated. There wasn't one gene, there were many, each contributing only a tiny amount. None capable of predicting sexual orientation by itself. Environment also mattered. Development mattered. Human biology turned out to be doing something much more complex than anyone expected. Instead of one switch, it looked more like thousands of tiny dials, each moving slightly, each interacting with countless others. And suddenly, the original question became even harder. How do you remove something when there isn't one thing to remove? For a long time, people assumed evolution worked like an engineer. Keep the useful parts, throw away the useless ones. Simple. Except evolution isn't an engineer. It's more like a gambler. It doesn't design perfect humans. It works with whatever already exists. Sometimes that means preserving traits that don't make sense on their own, because they're connected to dozens of others that do. Scientists see this everywhere. The same genes that increase the risk of one disease might also improve your immune system. Genes linked to creativity can also increase the likelihood of certain mental illnesses. Nature rarely trades one thing for nothing. Everything comes as a package. That may be exactly what's happening here. Some researchers think the genes influencing sexual orientation also affect personality, empathy, sociability, emotional sensitivity, creativity. The challenge is proving it. Human behavior is incredibly difficult to reduce to a single biological explanation. Every answer creates more variables, and every variable creates another question. Then, researchers noticed something even stranger. Human sex isn't only about reproduction. That sounds obvious today. But from an evolutionary perspective, it's unusual. Most mammals mate during short periods when reproduction is possible. Humans don't. Sex happens throughout the year. It strengthens relationships, builds trust, repairs conflict, creates emotional bonds. Long before anyone understood hormones, our ancestors were already using intimacy for far more than producing children. Why? Nobody knows exactly when that happened. But once sex became part of social life, the equation changed. It wasn't simply about making babies anymore. It became part of cooperation, part of attachment, part of belonging. Our closest living relatives offer another clue. Bonobos share almost all of our DNA. They also use sexual behavior in ways that have very little to do with reproduction. They calm arguments, reduce tension, strengthen alliances, welcome newcomers, reconnect after conflict. To them, sex is communication, not just reproduction. Humans are obviously different. Our societies are more complicated. Our relationships are more complicated. But we're still primates. And that raises another uncomfortable possibility. Maybe people have been asking the wrong evolutionary question. Instead of asking, why does homosexuality exist? Maybe the better question is, why do humans assume every form of sexuality must exist only to produce children? That assumption makes sense today. It doesn't necessarily describe the past. For most of human history, survival depended on stable groups. Groups held together by trust, cooperation, friendship, shared responsibility. Children survived because dozens of adults invested in them, not because two parents did everything alone. In a world like that, every member of the group mattered. The hunter, the healer, the storyteller, the person who remembered where water could still be found after months of drought. Evolution isn't counting births every afternoon. It's measuring something much larger. Which groups survive? Which groups disappear? And sometimes, those aren't the same thing. That still doesn't completely answer the question. Because the biggest mystery remains. If scientists have been studying this for decades, why hasn't anyone solved it? The answer is surprisingly simple. Human sexuality may be one of the most complicated traits we've ever tried to understand. Height is easier, eye color is easier, blood type is easier. Sexual orientation sits at the intersection of genetics, development, hormones, environment, and experiences we still don't fully understand. Researchers have identified genetic influences, but no single genetic cause. They've proposed evolutionary models. None explains every observation. They've studied identical twins. Even identical DNA doesn't always produce identical outcomes. The closer scientists look, the more complex the picture becomes. And complexity isn't failure. Sometimes it's exactly what we'd expect from a species as socially complicated as ours. There's another reason this question fascinates people. It challenges how most of us think evolution works. We like simple stories. Every trait must have one purpose. Every behavior must have one explanation. Reality refuses to cooperate. Evolution doesn't produce perfect answers. It produces populations. Variation isn't a mistake. Variation is often the reason populations survive. If every human thought exactly alike, reacted exactly alike, or behaved exactly alike, our species would probably be far less adaptable than it is today. Nature rarely bets everything on one strategy. It spreads its chances. That's true for bodies, for personalities, for behavior, and perhaps for sexuality too. The truth is, scientists still don't know exactly why homosexuality exists. Not because nobody has looked, because every discovery reveals another layer underneath it. It's one of those questions where certainty becomes harder, not easier, the more evidence we collect. What we do know is this: homosexuality isn't something that suddenly appeared in modern society. It isn't something created by the internet, or cities, or recent culture. The evidence points in the opposite direction. Same-sex attraction has been part of humanity for as long as we can trace humanity itself. It appears throughout recorded history. It appears across cultures that never met one another. It appears throughout the animal kingdom. Whatever its ultimate evolutionary explanation turns out to be, it's far older than civilization, far older than agriculture, possibly as old as our species itself. Which means the real mystery was never, why are some people gay? The mystery is why evolution, after hundreds of thousands of years, still sees absolutely no reason to erase one of humanity's oldest traits. Human behavior isn't the only mystery evolution leaves behind. A few years ago, some psychology researchers at the University of Virginia ran an experiment that basically proved our brains are completely broken. They wanted to see how people handled just being alone with their own thoughts. So they took normal, healthy adults, put them in a completely empty room, and told them to just sit there and think for 15 minutes. They took away their phones, their watches, their books, everything. It was just a chair and blank walls. But the researchers gave them one other option. On the table next to the chair was a button, and the researchers told them, if you push this button, you will receive a painful electric shock. They even gave the participants a sample shock beforehand, just to prove that, yes, it actually hurts. Logically, sitting quietly in a room is completely harmless. You just sit there, chill out, and wait for 15 minutes to pass. But the psychological agony of having absolutely nothing to do was apparently so unbearable that 67% of the men and 25% of the women willingly chose to shock just to make the boredom stop. One guy actually hit the button 190 times. In 15 minutes, people would literally rather feel physical pain than feel bored. And if you look at the animal kingdom, resting is the ultimate biological goal. Calories are the currency of survival, and they are incredibly hard to find. Spending your currency when you don't have to is a fast track to starvation. For example, a lion will happily sleep for 20 hours a day, or a snake can sit perfectly still under a rock for a week and be totally content. If they aren't actively hunting, running away from a predator, or trying to mate, the smartest thing they can possibly do is just sit perfectly still and conserve their energy. Evolution usually rewards laziness. So why do we feel actual, agonizing psychological pain when we're just sitting in a safe, low-energy state? Honestly, if we didn't, we probably would have gone extinct a long time ago. We usually think of boredom as just a blank space in our day. We think of it as the absence of a feeling, like our brain has just been put on standby. But neurologically, boredom is a highly aggressive, active alarm system. Think about physical pain. Physical pain evolved to make you pull your hand off a hot stove to save your tissue from being destroyed. Boredom evolved to make you pull your brain away from a dead end to save you from starvation. In behavioral ecology, there is this massive problem that every animal faces, and it's called the explore versus exploit trade-off. Imagine an early human ancestor finds a massive berry bush. At first, it's great. They sit there and eat, exploiting the resource. But eventually, the berries are going to run out. The question is, at what point do you leave the bush you know to go look for a bush you don't know? If you leave too early, you waste a bunch of energy wandering around the forest when you didn't need to. But if you stay too long, the food completely runs out and you starve before you can find the next meal. Evolution needed an internal timer. It needed a biological engine that would force us to constantly push the boundaries of our environment, even when we were already perfectly safe and fed. That engine is your dopamine system. A lot of people think dopamine is the pleasure chemical, but it's really not. It's the pursuit chemical. When you discover something new, your brain gives you a hit of dopamine. It feels incredible. But human brains are ruthlessly designed so that our dopamine baseline drops very quickly once we figure something out. As soon as a situation becomes predictable, your brain stops rewarding you. The dopamine dries up. That sudden chemical drop is what you actually feel as boredom. It feels bad on purpose. It's basically a biological cattle prod. Boredom is literally the reason humans spread out of Africa and covered the entire planet. It's the reason we didn't just stay in one valley until we ate everything and died. Boredom forces invention. It forces migration. But the craziest part about boredom is what actually happens inside your head when you feel it. When you sit in a quiet room with nothing to do, you might think your brain powers down. But neuroscientists have found that when you stop focusing on an outside task, a massive, highly connected network in your brain turns on. It's called the default mode network. When you get bored, your default mode network kicks into overdrive. It starts running simulations. It pulls up memories from your past. It projects scenarios into your future. It starts connecting completely random ideas that have nothing to do with each other. Your brain hates being understimulated so much that when the outside world stops providing novelty, your brain forces itself to generate its own internal novelty. This is exactly why your best ideas always happen when you're taking a shower. Your default mode network takes over and starts smashing random thoughts together just to keep itself entertained. That process is the literal definition of human creativity. You cannot have deep, creative insights without first passing through a layer of boredom. Your brain is still using boredom to say, "This environment is tapped out, go invent something." But we don't live in the Paleolithic woods anymore. We live in the 21st century, and we've invented the ultimate biological cheat code, doom scrolling. We have engineered an environment that completely short-circuits our evolutionary alarm system. Social media algorithms, video games, and streaming apps are perfectly designed to exploit our craving for novelty. They deliver micro hits of dopamine every 3 seconds. You feel the pain of boredom. You swipe your screen. In biology, this is called a supernormal stimulus. It's an artificial trigger that is so highly exaggerated that it completely overrides our natural instincts. Our phones are basically junk food for the explore and exploit drive. Your brain thinks you are out there discovering massive amounts of new territory and new social connections, but really you're just sitting on a couch, swiping your thumb. And we've started treating boredom like a disease that has to be cured the second we feel it. But by constantly medicating our boredom with cheap digital novelty, we are entirely bypassing the discovery phase. Think about how hard it is to sit down and read a book, or learn to play an instrument, or write a script. Those things require sustained attention, and in the beginning, they are incredibly boring. The dopamine reward doesn't come until much later after you've put in the work. Our dopamine baseline gets so skewed by rapid-fire content that reality starts to feel agonizingly slow. We lose our tolerance for the friction that is required to achieve anything difficult. We don't have to entertain ourselves anymore because the screen does it for us. But when the screen does the entertaining, the default mode network stays quiet. We are taking the exact biological fuel that built civilizations, and we're just burning it on 15-second videos. Please, after watching this video, let's both put our phones down, sit with our minds, get bored for at least half an hour. Who knows? Maybe you come up with an invention the world really needs. Even our emotions come with unexpected trade-offs. The biggest lie we are told about growing old is that it is just basic physics. We are taught that the human body is like a car. You drive it for long enough, the parts experience wear and tear, the engine rusts, and eventually the whole machine just breaks down. It sounds perfectly logical, but from a biological standpoint, it is completely false. A car cannot heal its own cracked windshield. A car cannot stitch its own tires back together. Your body is not a passive machine. It is a dynamic, self-healing organism that is constantly rebuilding itself from the inside out. Your biology absolutely knows how to repair broken DNA, clear out toxic waste, and regenerate dead cells. If you want proof that biological immortality is possible, look at the ocean. Turritopsis dohrnii is a tiny species of jellyfish that can literally revert its cells back to a youthful state whenever it gets injured or old. It hits the biological reset button over and over again, completely bypassing death. Or look at the Greenland shark, an animal with the exact same vertebrate building blocks as us, that routinely lives to be 500 years old. Nature completely understands how to build a body that doesn't age. So the paradox is, why did evolution deliberately turn off our repair mechanisms? If natural selection's only goal is to maximize our survival, why did it actively engineer a self-destruct sequence into our DNA? To understand that, you have to realize that death by old age is actually a genetic invention. For the first few billion years of life on Earth, organisms were just single-celled bacteria. And bacteria doesn't age. They just divide into two new identical cells, practically forever. Aging was only invented when multicellular life evolved, and it was invented because of a brutal evolutionary concept known as the disposable soma theory. Proposed by British biologist Thomas Kirkwood, the theory breaks down the mathematics of biological energy. Every organism has a strictly limited amount of energy, and it has to split that energy between two things: repairing its own body, the soma, and reproducing. Evolution forces a trade-off. If an animal spends 100% of its energy repairing its own cells, it lives forever, but it doesn't have any energy left over to make babies. If it has no babies, a predator will eventually eat it, and its genetic line goes extinct. So, natural selection struck a ruthless bargain. It decided that the most efficient way to pass on genes is to invest heavily in reproduction, and only invest just enough energy into repairing the body to keep it alive until the babies are born. Evolution doesn't view your body as a permanent temple. It views your body as a disposable temporary vehicle. Once the vehicle successfully delivers the genetic payload to the next generation, evolution stops paying for the maintenance. Biologists call this the selection shadow. Natural selection is incredibly powerful, but it is entirely focused on getting you to reproductive age. If a genetic mutation causes a fatal heart defect in a 10-year-old, that mutation is violently scrubbed from the gene pool because the child will never pass it on. But what if a mutation causes severe Alzheimer's disease at age 80? By the time the Alzheimer's triggers, that person has already had children and passed the gene to the next generation. Because the biological damage happens after the reproductive window has closed, natural selection is completely blind to it. It drops you into a shadow where late-life genetic flaws are allowed to silently accumulate. But the story gets much darker than just evolutionary neglect. Evolution doesn't just ignore you when you get old. It actively trades your future health for your present survival. This brings us to the most vital concept in aging research: antagonistic pleiotropy. This theory states that natural selection will actively favor a gene that gives you a massive survival advantage when you are young, even if that exact same gene destroys your body when you are old. The ultimate chilling proof of this is happening inside your cells right now with a specific gene called TP53. TP53 is often called the guardian of the genome. It is one of the most important tumor suppressor genes in the human body. When you are in your 20s and 30s, your cells are constantly dividing, and sometimes they make mistakes. When a cell starts mutating and threatens to turn into a deadly cancer, TP53 spots it and triggers a process called cellular senescence. It permanently disables the cell so it can never divide again. This mechanism is a biological superpower. It is the reason you don't instantly die of aggressive cancers in your youth. But there is a fatal catch. Over decades, as TP53 ruthlessly locks down damaged cells to protect you, those senescent cells start piling up in your tissues. Biologists call them zombie cells. They refuse to die, but they stop doing their jobs, and worse, they secrete highly toxic inflammatory chemicals into your bloodstream. By the time you're in your 70s, your tissues are absolutely swamped with these toxic zombie cells, draining your stem cell reserves and directly causing cardiovascular disease, arthritis, and organ failure. The exact same cancer-fighting mechanism that saves your life at 25 is the mechanism that causes your organs to decay at 75. Evolution looked at that trade-off and accepted it. It happily traded your late-life health to ensure you survived long enough to have kids. But this brings us to the ultimate question. If we have the technology in the future to cure these diseases, to clear out the zombie cells, and to turn the repair mechanisms back on permanently, what would happen if humans actually achieved biological immortality? In the 2020s, researchers at Harvard's Wise Institute and the New England Complex Systems Institute ran massive spatial computer simulations to answer this exact question. They built an artificial environment with limited resources and gave the simulated organisms the genetic ability to live forever. The results were catastrophic. Without aging, the immortal individuals never died. They just kept consuming food and taking up physical space. Because they refused to leave, they completely outcompeted their own children. They drained the local environment of every available resource. The population collapsed, and the entire lineage starved to death and went extinct. The computer models revealed a deeply profound reality. For a species to survive long-term in a world with limited resources, natural selection must enforce an optimal, limited lifespan. An active mechanism of programmed deterioration is mathematically required to prevent a generation from destroying the resources needed by its descendants. When you look at the absolute cutting edge of evolutionary biology, the paradox of aging vanishes. You do not age because your cells are just too fragile or because the universe is wearing you down. You age because evolution deemed your eternal survival less important than the survival of your children. The warranty on your biology expires because the energy required to keep you young is better spent creating new life. Aging is not a disease, it is not a mechanical failure, and it is not an accident of physics. It is the ultimate evolutionary sacrifice. Our bodies are intentionally designed to fade away, stepping aside, so the next generation has the space, the resources, and the chance to survive. And some compromises are impossible to ignore. If you look across the entire animal kingdom, giving birth is generally a straightforward, relatively quick biological event. A chimpanzee will often slip away into the brush, deliver her baby completely alone, clean herself up, and rejoin the group within a matter of hours. A horse can give birth to a foal that stands up and walks within 30 minutes. But for humans, childbirth is a monumental physical ordeal. For thousands of generations, it was one of the leading threats to a human being's survival, requiring immense physical agony, high structural risks, and mandatory assistance from the surrounding group. This presents a massive, baffling evolutionary contradiction. The primary directive of natural selection is to reproduce and successfully pass on your genetic material to the next generation. If survival of the fittest is the absolute law of nature, why did evolution make the very mechanism of human reproduction so incredibly dangerous? Why would natural selection hard-code a structural design that actively threatens the survival of both the mother and the infant at the exact moment life is being passed on? The immediate assumption is that human anatomy is simply a series of structural mistakes. But evolutionary biology and physical anthropology reveal that the danger of childbirth isn't a design flaw. It is the direct consequence of a high-stakes compromise, a biological treaty signed millions of years ago between the mechanics of how we walk and the size of our brains. To understand why this boundary exists, we have to look at the mechanical revolution that separated our ancestors from every other primate on Earth: bipedalism. Around 4 million years ago, our ancestors left the trees and began walking permanently on 2 legs. Moving upright across the African savanna was an incredible survival strategy. It freed up our hands to carry tools, lowered the surface area of our skin, exposed to the blistering midday sun, and allowed us to travel massive distances using a fraction of the metabolic energy required by a 4-legged ape. But walking upright required a total structural overhaul of the skeleton, particularly the pelvis. To support the weight of the upper body, and balance efficiently on two limbs, the human pelvis had to drastically change shape. In four-legged primates, the pelvis is long, flat, and open, creating a wide, straight birth canal that allows a baby to pass through effortlessly. But to walk upright, the human pelvis had to shrink. It became short, compact, and bowl-shaped. This structural tightening brought the hip joints closer to the center of gravity, making walking highly efficient, but it simultaneously compressed the internal birth canal, turning a spacious highway into a tight, twisted bottleneck. For a long time, this compressed pelvis wasn't a lethal problem because our early ancestors still had relatively small brains, roughly the size of a modern chimpanzee's. But around 2 million years ago, a secondary evolutionary explosion occurred. The human brain began to rapidly expand, ballooning to 3 times its ancestral size. This cognitive expansion turned us into the most dominant apex predators on Earth, allowing us to master fire, invent complex tools, and outsmart every competitor. But this sudden brain growth created an absolute anatomical crisis. Our brains were expanding exponentially, requiring larger and larger skulls, while our pelvic architecture was locked in place, tightly constrained by the physical laws of walking upright. This structural collision created what anthropologists call the obstetric dilemma. Natural selection was caught in a brutal tug-of-war. If the pelvic opening widened any further to accommodate a larger infant head, the mechanical leverage required to walk upright would be ruined, rendering the mother completely incapable of escaping predators or foraging for food. But if the infant's head grew any larger inside the womb, it would become physically impossible to pass through the tight, bony pelvis, resulting in immediate catastrophe for both. To solve this deadlock, evolution did something radical. It dramatically altered the human timeline of pregnancy. Almost every other mammal stays in the womb until their brain is relatively mature. A baby chimp is born with a brain that is already 40% of its adult size, allowing it to actively cling to its mother's fur for safety from day one. If a human baby stayed in the womb until its brain reached that same level of development, pregnancy would have to last for an impossible 21 months. By the time the baby was ready to be born, its head would be physically twice the size of the pelvic opening. So evolution forced human babies to be born completely premature. Human infants are delivered into the world when their brains are just 28% of their adult size. We are essentially born as external fetuses, completely helpless, unable to sit up, lift our own heads, or survive without 24-hour care. This early delivery is the only reason our heads can squeeze through the pelvic bottleneck at all. But even with this premature exit, the physical mechanics of human birth remain a high-stakes engineering puzzle. In chimps, the birth canal is straight and wider than the baby's head, meaning the infant slides through facing forward, allowing the mother to easily pull the baby up toward her chest without twisting its spine. But the human birth canal is so compressed and distorted by bipedalism that it actually changes shape halfway through. The entry point is wide from side to side, but the exit point is wide from front to back. This forces the human infant to perform a highly complex, hazardous series of physical maneuvers inside the pelvis known as rotational birth. The baby's head must enter the pelvis sideways, rotate 90 degrees mid-transit to align with the changing shape of the bone, and exit the birth canal completely backwards, facing away from the mother. Because the baby emerges backward, a human mother cannot safely reach down to guide the baby out herself without risking snapping the infant's neck or pulling against the natural curve of its spine. This mechanical limitation forced our species to develop a behavior that is completely unique in the animal kingdom: obligate midwifery. Throughout ancient history, humans could rarely give birth safely alone. We required a cooperative social network, midwives, family members, and tribal allies, to physically assist in the delivery, clear the infant's airway, and guide it safely through the final rotation. Childbirth didn't just test our physical limits, it directly forced the evolution of human empathy, social cooperation, and community bonding. Furthermore, recent metabolic research has revealed that the timing of human birth isn't just restricted by bone structure. A groundbreaking framework known as the energetics, gestation, and growth hypothesis shows that human pregnancy hits a hard metabolic ceiling. Growing a massive, large-brained infant requires an astronomical amount of energy from the mother's body. By the 9-month mark, the baby's metabolic demands reach a point where the mother's body physically cannot pump calories, oxygen, and nutrients into the placenta fast enough without triggering systemic organ failure for herself. 9 months isn't just the structural limit of the pelvis, it is the absolute red line of human metabolic endurance. To make this high-stakes process even remotely possible, natural selection hard-coded a final, fascinating structural trick into our infants: unfused skulls. Human babies are born with their cranial bones completely separated by soft, flexible gaps called fontanelles. During the intense pressure of labor, these skull plates are designed to physically slide past one another, actively compressing and molding the shape of the baby's head into a temporary cone shape just to squeeze through the narrow pelvic exit. Natural selection faced a brutal, uncompromising mathematical trade-off when designing human anatomy. It could have left us with wide, open primate pelvises, making childbirth completely safe and effortless. But we would still be shuffling around on all fours, unable to build tools, travel long distances, or outrun danger. Or it could have kept our brains small and simple, ensuring our heads easily cleared the birth canal, but we would have never developed language, culture, or the intelligence that allowed us to conquer the planet. Instead, evolution chose to maximize both traits, pushing the human body to the absolute structural and metabolic edge. It gave us the unmatched efficiency of walking upright and the limitless power of a massive brain, accepting the extreme physical price of dangerous cooperative childbirth as the necessary toll for our species' dominance. We didn't inherit a dangerous reproductive system because our biology is broken or flawed. We inherited it because we are a species built on extreme adaptations. The danger of childbirth is the permanent historical monument to our greatest evolutionary achievements, proving that the very vulnerability of how we enter the world is the exact price we paid to inherit the Earth. Our bodies still carry the cost of our evolutionary past. If you open a standard high school biology textbook, human reproduction is often presented as a straightforward binary system. You inherit an XX or an XY chromosome. That genetic blueprint guides the development of your physical body, and that physical body aligns with your internal identity, driving the primary evolutionary goal of finding a mate and reproducing. But biology, especially human biology, is rarely that simple. When we look at human populations across history and across the globe, we see a vast spectrum of gender identities, including transgender and gender non-conforming individuals. From a strictly traditional evolutionary standpoint, which often focuses heavily on direct reproduction, this presents a fascinating scientific question. If natural selection favors traits that maximize an individual's ability to have direct biological children, how do variations in gender identity persist in the human gene pool? Before we look at the science, it is incredibly important to state that gender identity is a highly complex phenomenon. Currently, there is no single, universally accepted evolutionary explanation for it. Human brains and human societies are incredibly intricate, and trying to reduce human behavior to a single biological equation is almost always a mistake. However, when we look through the lenses of developmental biology, endocrinology, genetics, and evolutionary psychology, scientists have developed several compelling frameworks. And what these fields suggest is that transgender identities are not modern anomalies, nor are they biological mistakes. They are a natural expression of the vast, complex spectrum of human development. To understand the biology of gender identity, we first have to look at developmental biology and embryology. We are often taught that biological sex is a single switch flipped at conception, but the reality is that building a human is a multi-stage process, and the physical body and the brain develop on completely different timelines. In developmental biology, there is a leading model known as the organizational activational hypothesis. According to this framework, during the first trimester of pregnancy, around the 6-week mark, a fetus begins to develop its physical anatomy. This initial stage is heavily driven by the sex chromosomes, but the human brain is an entirely different biological project. It is incredibly complex and takes much longer to build. The neurological pathways associated with internal gender identity and certain behaviors do not begin their major sexual differentiation until much later, primarily in the second half of the pregnancy. This brain development is not strictly dictated by the chromosomes themselves. Instead, endocrinologists have found that it is heavily influenced by complex washes of hormones, like testosterone and estrogen, that cross into the fetal brain. Because the physical body and the brain differentiate months apart, they can be influenced by entirely different hormonal environments. If the hormonal signals during the second half of pregnancy differ in concentration or timing from the genetic signals of the first trimester, the development of the physical body and the neurological wiring of the brain can naturally diverge. Furthermore, genetic variations in hormone receptors can change how the brain absorbs these chemicals. This is not a defect. It is simply a reflection of how deeply complex mammalian development is. It highlights that biological sex and gender are not a simple binary, but rather a bimodal spectrum with widespread natural variation. But this brings us back to the evolutionary question. Even if we understand the biological mechanisms in the womb, why would natural selection preserve a developmental pathway that might reduce an individual's likelihood of having direct biological children? To explore this, evolutionary biologists look at the broader mechanics of how humans actually survived in the ancient world. In evolutionary science, there is a heavy focus on individual reproduction, but humans are obligate social primates. In the prehistoric environment, an individual human could not survive alone. Our primary survival strategy was the community. Therefore, evolutionary pressures didn't just shape individuals, they shaped the dynamics of the entire tribe. This leads to one of the most prominent theories in evolutionary biology regarding traits that don't directly lead to reproduction: kin selection, also known as inclusive fitness. Raising a human infant is incredibly difficult. Human babies are born completely dependent and require a staggering amount of calories, time, and protection over many years. If every single adult in an ancient tribe was exclusively focused on breeding and raising their own direct children, the group's resources could easily be stretched beyond their limits. Kin selection proposes that a family's genetics can actually be highly successful if some members of the family do not reproduce directly, but instead invest their time and resources into helping raise their siblings' children. In evolutionary biology, this is sometimes called the helper in the nest model. By acting as allo-parents, extra adults who provide food, protection and education, these individuals greatly increase the survival rate of their nieces and nephews. Because they share a significant amount of DNA with those children, they are still successfully passing their genetic lineage into the next generation. Researchers in evolutionary psychology have studied this dynamic in cultures that traditionally recognize gender-diverse individuals. For example, extensive anthropological research on the Fa'afafine, a recognized third gender population in Samoa, has shown that these individuals frequently exhibit significantly higher tendencies to invest resources and care into their nieces and nephews compared to other groups. While this is just one piece of the puzzle, it strongly suggests that the evolutionary math of kin selection could play a role in maintaining gender diversity within the human gene pool. Beyond resource sharing, anthropologists point to another major evolutionary advantage: social cohesion. When we look at the historical and anthropological records, gender-diverse people have been documented in civilizations all over the world. We see the two-spirit people in various indigenous North American cultures, the Mahu in Hawaii and the Hijra in India, among many others. In many of these historical contexts, these individuals were highly respected and fully integrated into the community. Psychologists and anthropologists hypothesize that in early human societies, which often had strictly divided labor and social roles for men and women, gender-diverse individuals served a vital sociological function. Because they possessed a perspective that bridged the gap between traditional male and female roles, they often acted as mediators, healers, and spiritual leaders. In a highly volatile prehistoric environment, a tribe that possessed individuals who could navigate different social spheres and reduce internal conflicts had a distinct survival advantage over tribes that were rigidly divided. Finally, geneticists offer another important framework known as antagonistic pleiotropy. This is the idea that a specific gene or a set of epigenetic factors can have multiple different effects on a population. It is entirely possible that the genetic or epigenetic factors that contribute to gender diversity provide other highly beneficial reproductive or survival advantages to the individual's family members. For example, a genetic factor that leads to a transgender identity in one child might simultaneously increase the overall fertility, immune strength, or cognitive empathy of their siblings. In this scenario, evolution preserves the genetic underlying factors because the net benefit to the family line as a whole is overwhelmingly positive. Ultimately, the science of gender identity is an active, evolving field. We may never have one single, perfectly neat mathematical equation to explain human gender diversity, precisely because human beings are not simple machines. But what the fields of biology, endocrinology, and anthropology collectively show us is that variation is a fundamental law of nature. A population where every single individual is genetically and neurologically identical is incredibly fragile. Our species' strength has always relied on a vast spectrum of physical traits, cognitive abilities, and social roles. Transgender and gender-diverse people are a deeply rooted part of the human story. Their presence in the historical record and the biological mechanisms that guide their development remind us that evolution relies on diversity to build resilient, complex societies. They are not an anomaly of modern culture, but a natural reflection of the remarkable complexity of human biology. Evolution doesn't always move in the direction you'd expect. Here's a sentence that sounds like it shouldn't be true. At some point in the last few tens of thousands of years, the human brain got smaller. Somewhere around 10% of its volume gone. Line up a skull from an Ice Age human next to a modern one, and the ancient one is noticeably bigger. We're talking about losing roughly the volume of a tennis ball off the top of the most complex object we know of in the universe. For millions of years, the story of the human brain only moved one direction, and that's the version most of us grew up hearing. Bigger brain, smarter species, more tools, more art, more everything. Then, somewhere along the way, it reversed. And scientists still don't agree on when this happened, why it happened, or whether it even means anything bad. So I went looking for the answer. What I found instead was a live scientific argument, researchers publicly contradicting each other. So let's go through it properly. Who are the suspects? First, the boring explanation, because it deserves a fair hearing. Brains don't exist in isolation. Bigger bodies generally need bigger brains just to run them, more muscle to coordinate, more sensory surface area to process. So the simplest idea is that human bodies got smaller after the Ice Age, likely as diets shifted with the spread of farming, and the brain just came along for the ride. No mystery, no decline in thinking, just proportional scaling. But the brain is an outrageously expensive organ to run. Despite being a small fraction of your total body weight, it eats up a hugely disproportionate share of your daily energy budget just sitting there thinking. Researchers Leslie Aiello and Peter Wheeler proposed something called the expensive tissue hypothesis to explain how humans could afford such a costly brain in the first place. Their answer: something else in the body had to get cheaper to compensate. And the organ that shrank to pay for it was the gut. As human diets shifted toward higher quality, easier to digest food, our digestive tracts could get smaller, freeing up energy that got redirected toward this incredibly expensive brain. So if energy is the whole story, and diets shifted again later in different directions, could the reverse have happened too? A body reallocating energy away from the brain this time. It's a clean, physiological explanation. The problem is, when researchers actually test brain shrinkage against body size changes in the data, the drop in brain size looks bigger than body size alone can explain. So something else is happening. Here's an idea that a lot of serious researchers take seriously, and it still catches people off guard the first time they hear it. Humans may have domesticated themselves. Look at almost any domesticated animal next to its wild ancestor: a dog next to a wolf, a farm fox next to a wild fox. There's a repeating pattern across totally unrelated species: smaller skulls, smaller teeth, softer and more youthful-looking faces, less aggression, and very often smaller brains. Researchers Brian Hare and Richard Wrangham have argued that something similar happened to us, just without a human breeder making the choices. Their idea is that early human groups increasingly punished extreme aggression from within. A violently dominant individual was more likely to get ganged up on and removed from the group than to thrive and reproduce. Do that consistently, generation after generation, and you've got a real selection pressure, the same kind that shapes domesticated species elsewhere. Except here humans did it to themselves, through social punishment instead of a breeder's hand. And the skeletal evidence lines up in a genuinely eerie way. Human skulls do get less rugged and more juvenile looking across this window. Brow ridges shrink. Faces get shorter and softer. Some researchers connect this to lower testosterone exposure during development, echoing changes documented in animals deliberately bred for tameness. The most famous version of that comparison is a real, decades-long experiment in Siberia. Starting in 1959, geneticist Dmitry Belyaev and later his colleague Lyudmila Trut bred silver foxes for exactly one trait: calmness around humans, just tameness. Within a handful of generations, entirely new traits started showing up that nobody had selected for directly. Floppy ears, curly tails, patches of white fur, faces that stayed puppyish into adulthood. It's one of the most famous demonstrations in biology that selecting for one behavioral trait can drag a whole cluster of physical traits along with it. So naturally, everyone assumed brain size would shrink in those tame foxes too, matching the classic domestication pattern. Except when researchers actually scanned the brains of those tame foxes in detail, that's not quite what they found. The tame foxes didn't show reduced brain volume at all. If anything, certain brain regions were larger compared to ordinary farm-bred foxes. Even stranger, foxes bred for the opposite trait. Heightened aggression showed some of the same neural changes. So even the flagship experiment behind the domestication shrinks the brain idea turned out to be more complicated than the simple version everyone repeats. Selecting for tameness clearly rewires the brain. It just isn't obviously the same thing as shrinking it, which means suspect 2 isn't cleared exactly, but it's not an open and shut case either. So on to the next suspect we go. A team of researchers proposed something almost sideways to the other explanations. Maybe individual brains got smaller because human societies got smarter, not less intelligent people. Less need for any one person to carry the full cognitive load alone. Here's a way to picture it. Imagine two people, Bob and Alice, living in very different kinds of groups. Bob lives in a small, isolated band. If Bob doesn't personally know how to track an animal, treat a wound, start a fire, navigate by the stars, and remember which plants are poisonous, nobody's necessarily around to fill that gap for him. His own head has to hold almost everything his survival depends on. Alice lives generations later, in a much larger, more interconnected society, with trade routes, specialists, and shared knowledge passed between groups. Alice doesn't need to personally know how to do everything. Someone else in her network is the healer. Someone else is the toolmaker. Someone else studies the stars. Alice can lean on the network instead of carrying it all herself. The researchers behind this hypothesis leaned on an unusual comparison to make their case: ant colonies. In some ant species, individual ants actually have smaller brains than their solitary ancestors, even as the colony as a whole becomes capable of dramatically more complex coordinated behavior. When a group starts sharing information, dividing labor and specializing, no single member needs to personally hold everything in their own head. Intelligence starts living in the network as much as in any one individual. Applied to Alice's world instead of Bob's, that's a genuinely elegant idea. And then another team of researchers came along and picked the whole thing apart. A separate group went back to the same kind of fossil evidence and reached a strikingly different conclusion. No meaningful brain size reduction at all across the entire recorded history of our species. Their critique was pointed and specific. The original sample size covering the critical time window was small, just a couple dozen skulls. Those skulls were pulled from wildly different parts of the world and lumped together, as if agriculture, social complexity, and diet had all changed everywhere on Earth at exactly the same moment, which they demonstrably didn't. And if the outsourcing knowledge to complex societies idea were correct, you'd expect the timing of any brain shrinkage to differ region by region, depending on when complex societies actually showed up locally. Their reanalysis found no such regional pattern, and no statistically significant reduction at all. For a while, this looked like case closed. Verdict, myth. Except the case didn't stay closed. More recently, a much larger analysis revisited the whole question, using nearly 1,000 skulls instead of a couple dozen. And it landed on brain shrinkage again, but with a genuine plot twist. The timing wasn't 20 or 30,000 years ago at all. It pointed to something far more recent, only around 3,000 years ago, well inside recorded history, somewhere around the era of early empires and the spread of writing systems. And that same research team directly tested whether body size, diet, or self-domestication could explain the drop. According to their own analysis, none of those fully accounted for it, which quietly puts even the earlier suspects back on trial, including the very domestication idea we just spent several minutes on. So, where does that honestly leave us? Two credible research teams, two very different timelines, a genuine, ongoing, public disagreement about whether this even happened, let alone why. That's not the tidy ending I went in hoping to find, but it might be the most honest one available right now. Before this spirals into an existential crisis about your own skull, here's something worth sitting with. Even researchers who are confident the brain shrank are quick to say that doesn't mean modern humans think worse than Ice Age humans. Brain size and intelligence just aren't the same measurement. Women's brains are, on average, smaller than men's, with no corresponding gap in cognitive ability. And going back further, Neanderthals, our closest extinct relatives, actually had larger average brain volumes than modern humans do, without clear evidence that translated into greater intelligence. Some researchers argue a smaller brain could simply be a more efficient brain. Better organized wiring, doing more with less raw material, similar to how a modern processor can outperform a bulkier one built a decade earlier. So, even inside the "yes, it genuinely shrank" camp, the interesting question isn't, are we getting dumber? It's what actually changed inside the wiring, not just the outer size. And that question is still wide open. Isn't the newest study just going to get refuted too, the same way the last one was? Maybe. That's a completely fair thing to wonder, and honestly part of why this topic is worth revisiting. Science working exactly like this, with claims getting tested, challenged, and retested against bigger data sets, isn't a sign the field is broken. It's what a live, unresolved question is supposed to look like from the outside. If we self-domesticated, shouldn't that show up clearly in brain scans the way it did in the tame foxes? You'd think so, and that's exactly the problem the 2021 Fox study raised. It didn't cleanly show up the expected way, even in the textbook domestication experiment, which is a real complication for anyone treating self-domestication as a settled explanation for smaller human brains. Could this trend still be happening right now, or could it reverse? There's no strong evidence either way, and this is genuinely hard to track in real time. Confidently measuring skull trends takes centuries of accumulated data, not decades. So the next time somebody tells you with total confidence that the human brain has been shrinking for thousands of years, you now know the honest version. It might be true, it might not be. And even the researchers chasing it down keep landing on different years, different causes, and different verdicts. Maybe we didn't get smaller because we got weaker. Maybe we got smaller because, for the first time in our history, we stopped needing to carry everything alone in one skull. Or maybe we didn't get smaller at all, and we're just now organized enough as a species to keep arguing about it properly. Evolution didn't just change our brains, it also left us with abilities we never regained. A salamander gets its arm bitten clean off by a predator. Give it a few weeks, and it just grows a new one. Bones, muscle, nerves, skin, no scar, fully functional, wiggling its new fingers like nothing happened. Now picture a human losing a finger. Best case, with incredible medical care, you get a scar. We share the same basic body plan as this animal. Same bones in roughly the same places. Same kind of blood. Same kind of nerves. So why does one of us get a free replacement limb and the other gets a very expensive bandage? I expected the answer to be something simple. Like, salamanders just have a special gene we don't. What I actually found was that your body might not be unable to do this, but that it might be refusing to. So, let's start where I started. With the one animal that made this whole question worth asking. How does a salamander pull this off? There's a structure called a blastema. When an axolotl loses a limb, cells near the wound don't just start dividing. They partially forget what they were. A muscle cell stops acting like a muscle cell. A skin cell stops acting like a skin cell. They pile up into a small mass at the injury site, and from there they rebuild, in order, into a brand new limb. Researchers have described it almost like rebuilding a factory after an earthquake. Debris gets cleared first. That's the immune system doing cleanup. Then, specialized crews move in. One team lays down bone, one builds muscle, one threads through blood vessels, one rewires nerves. piece by piece, until the whole structure is standing again, fully wired, fully working, and it's not sloppy. It's not a rough draft of an arm. That's the local repair job. Except it turns out that's not actually what's happening. I assumed regeneration was a wound site event. Damage happens, nearby cells respond, done, contained, local. Like a splinter. Then, a 2025 study found that when an axolotl loses a limb, the signs of that injury show up almost everywhere in its body. Not just at the wound, limbs that were never even touched light up with the same molecular signals. The animal's entire system seems to know something happened, and if an axolotl loses a second limb shortly after the first, it regrows that one faster. Like the whole animal had already gone on alert and preloaded the resources for round 2, just in case. So, what's coordinating something body-wide like that? Researchers traced part of it back to adrenaline, the same fight-or-flight chemical your body dumps when you're scared. Somehow, in the axolotl, that same chemical seems to help prepare cells throughout the body for regeneration before the actual rebuilding even starts. And because humans have that exact same adrenaline system, this isn't a purely salamander trick. We might already have some of the hardware sitting in us, unused. We just don't know how to switch it on the same way. An axolotl doesn't just regrow a limb, it regrows the correct amount of limb. Lose the whole arm, you get a whole new arm. Lose only a fingertip, you get only a new fingertip. Somehow, the blastema knows exactly how much to build and exactly where to stop. Researchers eventually found part of the mechanism behind that, a set of genes that function almost like a blueprint, plus an enzyme that fine-tunes exactly how much of the limb needs to be reconstructed. It's not a vague grow something here instruction. It's precise, down to the joint. One scientist who'd spent decades studying this admitted he used to be skeptical humans could ever do this. After the discovery, he said, "Now we have the blueprint, and we have the genes to grow a limb. That's a big claim to make out loud. So I went looking for whether humans have any version of that blueprint left in us somewhere. Before I get to the human part, it's worth pausing on something. This isn't as simple as some animals regenerate and some don't. There's a huge range, and humans sit near the bottom of it, which honestly stung a little to learn. At the extreme end, you've got flatworms called planarians. Cut one into pieces, and multiple pieces can each grow into a complete separate worm. Salamanders are nowhere near that extreme, but they're still the only vertebrates. Animals with a backbone like us that can regrow a fully functional limb. Lizards get partial credit. They can regrow tails, but if you look closely, it's not the same tail. It's usually a cartilage rod instead of a proper stack of vertebrae. And then there's an animal I hadn't even heard of before this rabbit hole, the African spiny mouse. It can lose huge sections of its own skin. Researchers have documented it losing something like 60% of the skin on its back, and grow it back with hair, glands and all, no scarring. Some species can even shed patches of skin on purpose to escape a predator's grip, the way a lizard drops its tail. So somewhere on that spectrum, worms that regrow their entire body, salamanders that regrow whole limbs, lizards that regrow an approximation of a tail, mice that regrow huge patches of skin, humans sit almost at the very bottom. Fingertips in children for a few years. Which brought me back to the real question, why there? Why only that? Human fetuses, for a window early in pregnancy, heel cuts completely scar-free. Then that window closes sometime before birth, and the scarring program takes over for the rest of your life. It doesn't fully stop there either. Young children can sometimes regrow the very tip of a finger, just the last few millimeters past the nail. This has been documented in clinical case reports going back decades. And the ability quietly fades as the child gets older, until one day it's just gone. So the question flipped on me at this point. It stopped being, why can't humans regenerate? and became something closer to why does this ability get switched off piece by piece as we grow up? A 2026 study asked a very specific version of this question. Why does only the very tip of a finger regrow, while the rest of the same finger can't? The answer centered on a molecule already sitting in your bathroom cabinet, if you own moisturizer: hyaluronic acid. Tissue, with more of it in the material surrounding the cells, regenerated more successfully. Tissue with less of it just defaulted to a scar, so humans didn't lose the ability to regenerate. We turned the dial almost all the way down and left it flipped on in one tiny spot for a few short years, in a place small enough that whatever risk comes with it is easy to manage. If the switch still technically exists somewhere in us, why would our own body choose to keep it turned off almost everywhere else for almost our entire life? Now imagine two people, Bob and Alice, both lose a hand in the same accident. Bob's body does what every adult human body does: inflammation, clotting, immune cells rushing in, and eventually scar tissue seals the wound shut. Permanent. His cells stop dividing once it's closed, and they stay stopped. Alice's body, in this hypothetical, does something closer to what a salamander does. Cells at the wound forget what they were, start dividing fast and begin rebuilding layer by layer the way a blastemer would. Sounds like Alice wins that trade, right? Except cells that divide rapidly while ignoring the body's normal stop growing now signal already have a name in medicine: a tumour. The exact kind of cells you'd need to rebuild an arm look alarmingly similar to the kind of cells that become cancer. Both are cells that have been told, one way or another, to stop listening to the rules and just keep multiplying. There's a real, long-studied strain of lab mice that proves this connection isn't just theory. These mice can punch a hole clean through their own ear, and it heals with no scar and full cartilage regrowth. Almost a mammal doing salamander-style repair in miniature. Researchers traced part of that ability to a gene called P21, a brake that normally stops cells from dividing out of control. In these particular mice, that brake is loosened, but only right at the wound. P21 has a much more famous relative, P53. The gene, sometimes nicknamed the guardian of the genome, because its entire job every day in every one of your cells is stopping damaged cells from turning into tumours. So the same brakes that are likely keeping your cells from regrowing a limb are, quite possibly, some of the same brakes keeping your cells from turning cancerous. Evolution may not have forgotten how to regrow limbs in mammals. It may have looked directly at the risk and decided against it on purpose, because a salamander in a pond can gamble on loosened growth control in a way that a human trying to survive 80+ years simply can't afford to. Scientists still don't fully understand every piece of this puzzle. Once I understood the trade-off, the next question was obvious. Could we ever get around it? Some of the more serious research money in regenerative medicine right now is aimed at exactly this. Not how do we grow a limb in a jar, but how do we get the benefits of regeneration without opening the door to cancer? That's a much harder problem than it sounds, because you're not looking for one switch to flip. You're looking for a way to loosen the brakes just enough, just locally, just temporarily, and then reapply them the second the job is done. Nobody has cracked that yet, not for a human limb. But it's worth sitting with how different that sentence is from where this field stood not that long ago. Can't we just gene edit our way back to this? People are trying, but it looks like human cells might not be able to forget what they are the same way axolotl cells do. It's not one switch. It's a whole coordinated process spread across the entire body, and we're still mapping the basic wiring of it. Is this just underfunded science that's about to get solved any day now? Partly funding, sure, but even the researchers closest to this work are cautious. Human limb regeneration is likely far off, and regrowing something as large and complicated as an adult arm could plausibly take years, not weeks, even once the underlying biology is fully understood. If cancer is really the risk, shouldn't regenerating animals be full of tumours? You'd think so, but it's messier than that in practice. Some of these regenerating mice look tumour-friendly in certain ways and unusually resistant in others at the same time. Scientists still don't fully understand why, and that inconsistency alone tells you this isn't a solved problem. So, will this ever actually happen for humans? Most researchers in this space would say, plausible eventually, not close right now. So next time someone jokes about wishing they could regrow a limb like a lizard's tail, tell them your body could probably still do a rough draft of that. Maybe evolution never forgot how to regrow an arm. Maybe it just chose you instead. Not every quirk gets removed by natural selection. If you're left-handed, I probably don't need to tell you that the world wasn't built for you. You figure that out pretty quickly the first time you try to use a pair of cheap scissors, or when you drag the side of your hand across fresh ink in a spiral notebook. Almost every piece of heavy machinery, every car console, every power tool, and every video game controller is aggressively tailored to a right-handed majority. And for a long time, the right-handed majority wasn't exactly nice about it either. Historically, being left-handed was treated with intense suspicion. If you look at the origins of our language, it's practically baked into the vocabulary. The English word sinister literally comes from the original Latin word for left. The French word for left is gauche, which we use today to describe someone who is socially awkward or clumsy. Right up until a few decades ago, left-handed children in schools were routinely punished. Teachers would physically tie a kid's left hand behind their back and force them to write with their right hand until they adapted. But human bias and annoying scissors are nothing compared to the actual biological puzzle of handedness. If you dig into the archaeological record, you'll find that early human ancestors were already making stone tools specifically designed for right-handed grips over 2 million years ago. And today, if you look across almost every single recognized culture, isolated tribe, and geographic region on the planet, the ratio of handedness is practically locked in stone. Roughly 90% of humans are right-handed. Exactly 10% are left-handed. For an evolutionary biologist, that 10% figure is a massive statistical headache. Evolution usually operates on some pretty straightforward math. If a genetic trait gives an animal a huge survival advantage, the animals with that trait live longer, they have more kids, and eventually the trait spreads until the entire species has it. On the flip side, if a trait actively gets you killed or makes it harder for you to survive, it gets violently scrubbed from the gene pool, the individuals who carry it die off, and the trait drops to zero. And if a trait is completely neutral, meaning it doesn't help you, but it doesn't hurt you either, the population should naturally split down the middle. It should be a 50-50 coin toss. Handedness isn't 50-50, and it hasn't dropped to zero. Natural selection has actively maintained this exact 90-10 ratio for hundreds of thousands of years. Why? To figure that out, we first have to kill a very old myth. For a long time, researchers assumed handedness was just a cultural habit. The thinking was that you watched your parents use their right hands, so you just naturally copied them. But modern science has completely debunked that. Being left or right-handed is deeply physically hardwired into your biology long before you even take your first breath. In fact, it happens before your brain is even connected to your body. Biologists have discovered that between just 8 and 12 weeks of pregnancy, the left and right sides of a fetus's developing spinal cord begin to express genes completely differently. The spine actually rigs the motor circuitry to favor one side before the brain even has a say. It's in the DNA. For years, scientists looked for one single left-handed gene, but recent massive genomic studies in 2025 and 2026 proved it's a huge team effort. Handedness is driven by over 40 different gene variants, specifically tubulin genes, which act as the microscopic scaffolding that physically shapes our cells as we grow. So why did evolution program the vast, overwhelming majority of us to favor the right side? Well, look at animals that aren't human. If you go into the wild and watch a group of chimpanzees or gorillas, you'll see them using their hands quite a bit. They crack open nuts with rocks. They fish for termites using sticks. But unlike humans, chimpanzees don't have a 90-to-10 ratio. The primate world is generally split right down the middle. Half are lefties, half are righties. The reason humans broke away from that 50-50 split, it comes down to two massive evolutionary shifts: walking on two legs and talking. In May 2026, a landmark study from the University of Oxford looked at over 2,000 primates to solve this exact mystery. They found that when our ancestors stood upright, it completely freed our hands from being used for walking. That created an intense new evolutionary pressure for specialized hand use. Right around the same time, our brains rapidly expanded and we developed complex language. Your brain is lateralized, meaning certain high-level tasks are processed strictly on one side. For most people, the left hemisphere is the control center for language and speech. Both talking and crafting tools require intense, rapid-fire cognitive processing. Neuroscientists believe evolution took a shortcut. It clustered these high-energy tasks, language, speech, and fine motor skills, tightly together into the left hemisphere to maximize processing speed. And because a weird quirk of anatomy means the left hemisphere controls the right side of the body, the human species became overwhelmingly right-handed. That neurological shortcut made right-handedness the default setting for human biology. And in a prehistoric hunter-gatherer tribe, being born with that default setting gave you a massive advantage. Early humans survived the Ice Age and apex predators through intense, synchronized cooperation. You had to share literally everything to stay alive. If your entire tribe uses identical right-handed spears, right-handed flint axes, and right-handed cutting tools, it creates a seamless survival economy. Anyone can pick up a fallen friend's weapon and instantly defend themselves without missing a beat. Beyond that, making ancient tools was actually a highly precise science. When a tribe sat around a fire knapping flint to make arrowheads, a right-handed strike flakes the stone in a very specific, predictable direction. If a left-handed napper picks up that same coarse stone and hits it from the opposite angle, it creates a completely different flake pattern. They would essentially ruin the tool for the rest of the right-handed tribe. Their weapons wouldn't match the group's standardized hunting equipment. In a prehistoric world, where a fraction of a second means the difference between taking down a wild boar or starving to death, being a left-handed outlier in a right-handed hunting party was a serious mechanical liability. The pressure to conform was immense. Under the brutal rules of cooperative survival, left-handers shouldn't exist. They should have been bred out of the population entirely. But humans don't just cooperate, we also fight. In 2005, a team of French evolutionary biologists named Dr. Charlotte Fourie and Dr. Michel Raymond were looking at this exact puzzle, and they proposed a groundbreaking idea called the fighter hypothesis. They realized that while being left-handed was a terrible disadvantage when you were trying to share tools with your friends, it was an absolute lethal cheat code when you were trying to kill your enemies. Picture two ancient warriors squaring off in hand-to-hand combat. Because 90% of the population is right-handed, a right-handed warrior spends his entire life sparring, training, and fighting against other right-handed people. His brain is completely neurologically hardwired to anticipate a punch, a swing, or a spear thrust coming from his opponent's right side. He knows exactly how to angle his shield. He knows exactly where to step to dodge the attack. A left-handed warrior is perfectly prepared for this fight too. Because he lives in a right-handed world, he has also spent his entire life fighting right-handed opponents. But the right-handed guy is completely blind to what is about to happen. When the left-hander attacks, the strike comes from a completely backward, totally unexpected angle. The right-hander's defensive muscle memory is entirely useless. His shield is in the wrong place. His footing is wrong. In life or death prehistoric combat, that split-second element of surprise is usually all it takes to win. This isn't just some abstract theory about cavemen. The fighter hypothesis is backed up by hard data, and you can actually watch this ancient combat advantage play out on live television today. Left-handers make up just 10% of the general population, but they massively dominate elite one-on-one sports. In professional fencing, tennis, and baseball, lefties frequently make up 30 to 50% of the top-ranked athletes. If you watch combat sports like boxing or MMA, fighting a southpaw is notoriously frustrating. Right-handed fighters simply aren't programmed to block strikes coming from a left-handed stance. But Forey and Raymond didn't just look at sports. They actually traveled to remote modern-day tribal societies that still engage in frequent violent physical conflict, like the Yanomami people in South America. They found a direct, chilling mathematical correlation. The higher the murder rate and the more violent the society, the higher the percentage of left-handed people surviving and passing on their genes in that population. The rules of ancient tribal warfare are still actively dictating human genetics. But this introduces the final and most important piece of the puzzle. If being left-handed makes you a lethal fighter, and winning fights allows you to survive and pass on your genes, why didn't left-handers just multiply? Why didn't they take over the world? Why are they eternally capped at 10%? It all comes down to a brilliant biological principle called frequency-dependent selection. In biology, frequency-dependent selection means that the survival value of a genetic trait depends entirely on how rare it is. The left-handed combat advantage only works because nobody expects it. If left-handers were highly successful and kept having kids until they made up 50% of the population, their evolutionary advantage would instantly vanish. Right-handers would spend half their time fighting left-handers. Their brains would adapt, their muscle memory would adjust, and the element of surprise would be completely gone. Evolution has locked human-handedness into a permanent, unyielding mathematical stalemate. If the left-handed population drops too low, say down to 2 or 3%, those few remaining lefties gain a massive, highly unpredictable advantage in combat. They easily defeat their right-handed rivals. They survive, they reproduce, and they push their population numbers back up. But if their numbers rise too high, say they hit 15 or 20%, they lose the element of surprise. The combat advantage evaporates, and suddenly, the cooperative disadvantages of living in a right-handed world start to weigh them down, pushing their numbers right back down to the equilibrium point. For hundreds of thousands of years, natural selection has perfectly balanced these two opposing forces. The intense pressure to share tools, coordinate hunts, and build cooperative societies pushes the human race toward the right, but the brutal, unavoidable reality of human conflict protects the left. That 10% ratio is the exact mathematical equilibrium where those two forces collide. So if you are left-handed and you find yourself struggling to use a cheap pair of right-handed scissors, or you're bumping elbows with someone at a crowded dinner table, don't curse your genetics. You aren't a biological mistake. You aren't a glitch in the system, and you aren't just a quirk of habit. You are the direct result of a highly sophisticated, millions of years old biological strategy. Natural selection intentionally preserved your neurological wiring to serve as a standing army of wildcards. Because in the brutal, unpredictable game of human survival, the greatest advantage you can possibly have is being exactly what the world doesn't expect. Which brings us to perhaps the clearest example of evolution's unfinished work. Evolution has had roughly 6 to 7 million years to work on the human spine since we split from our last common ancestor with chimps. That's plenty of time to fix a design flaw. So why does one of the most common medical complaints in the world come standard, built right into the human body plan? Your spine wasn't designed from scratch to hold you upright. It was inherited, then repurposed. For most of vertebrate history, a spine's job was to work like a horizontal beam, suspended between 4 legs, roughly the way a suspension bridge distributes weight between 2 supports. Picture a dog or a horse. Their spine mostly handles the same kind of bending and stretching forces you'd see in a beam. Then, somewhere around 6 to 7 million years ago, our ancestors stood up. And that same beam suddenly had to do something it was never originally built for: stack straight up, vertically, and carry the entire compressive weight of everything above it, straight down, onto 2 legs all day, every day, for decades. That's not a small tweak. That's closer to taking a bridge and asking it to also function as a load-bearing column, without redesigning it from the ground up. So how did evolution even attempt to solve that? The fix evolution landed on was elegant. On paper, your spine isn't straight. It curves in an S shape, alternating forward and backward through your neck, upper back, and lower back. That curve isn't decorative. It's what keeps your center of gravity balanced directly over your hips, instead of pitching your whole upper body forward. And this wasn't a modern human innovation either. Even some of our much older ancestors, going back millions of years, already show early signs of that lower back curve in their fossilized vertebrae. This adaptation has been under construction for an extremely long time. Sounds like a solved problem, right? A functional curve, doing its job. Except that curve comes with a catch that most people never hear about. Researchers studying human, chimpanzee, and orangutan vertebrae found something specific. The exact shape of individual vertebrae varies from person to person, and that variation isn't random. Some people's lower vertebrae are shaped in a way that's fully adapted to upright walking. Others, for reasons of individual variation, have vertebrae shaped closer to what you'd find in a knuckle-walking chimpanzee, even though they're just as human and just as upright. And the people whose vertebrae land closer to that ancestral chimp-like shape are significantly more likely to show signs of disc herniation. Not a small correlation, a meaningfully strong one replicated across multiple studies using both old skeletal remains and 3D bone scans. Picture 2 people, Bob and Alice, both healthy, both walking upright their whole lives. Bob's lower vertebrae happen to be shaped almost perfectly for the compressive stresses of bipedal walking. Alice's are shaped just slightly closer to the ancestral 4-legged version. Same species, same lifestyle, same posture. But Alice is carrying a spine that's still partway through an unfinished renovation, and her discs pay the price for it. So evolution didn't fail to solve this problem. It's still actively in the process of solving it, vertebra by vertebra, generation by generation. Some of us are just further along in that renovation than others, and disc herniation isn't even the only signature of this unfinished renovation. There's a specific kind of stress fracture called spondylolysis, where a small bony bridge in the back of a vertebra cracks under repeated load, sometimes letting one vertebra slip slightly forward over the one below it. Researchers studying the evolution of the human lower spine have connected this fracture directly to the mechanical demands of walking upright on 2 legs, And it shows up in the human skeletal record far more often than in our quadrupedal relatives. It's essentially a stress crack, forming in exactly the location you'd expect if a structure built for horizontal loading were suddenly asked to bear weight vertically instead. Which raises the obvious follow-up. If this fix has been in progress for millions of years already, why hasn't it finished? Astronauts are a walking, orbiting demonstration of exactly how much work gravity is quietly doing to your spine every single day of your life. Send a person to the International Space Station for several months, and they come home measurably taller. We're talking as much as 5 centimeters, roughly 2 inches on a 6-foot frame. That's not muscle growth. That's your spine, freed from gravity for the first time in your life, stretching out and straightening slightly, the way it was never able to on Earth. And it comes at a real cost. NASA has documented that the muscles supporting the spine noticeably weaken in microgravity, since they're no longer working constantly just to keep you upright against gravity. Roughly half of astronauts report back pain during their missions. And in the months after they land, astronauts face a documented risk of disc herniation that's been measured at over 4 times higher than in matched non-astronaut adults. Think about what that actually proves. Take away the one force your spine has spent millions of years slowly adapting to fight, even briefly, and the whole structure destabilizes almost immediately once it has to cope with gravity again. Your spine isn't just under construction, it's under constant, active maintenance, propped up moment to moment by muscles fighting gravity, so the underlying architecture doesn't have to be perfect. And here's the quieter, earthbound version of the same story. Starting around age 30, the discs between your vertebrae begin losing water content and gradually compressing. And most people measurably shorten by around 1 centimeter per decade for the rest of their life. You are right now on a very slow, very literal descent, the exact mirror image of what happens to an astronaut in freefall. Gravity built the problem. Gravity also never lets up long enough for evolution to declare the renovation finished. Evolution doesn't optimize for comfort. It doesn't optimize for your 50s, 60s, or 80s. It optimizes almost entirely for one thing: whether you survive long enough to reproduce and successfully raise offspring who do the same. And here's the detail that matters most. Global health data shows that back pain cases and disability from it climb steadily with age, peaking somewhere between 50 and 85 years old. That's well past the reproductive window for most of human evolutionary history. A spinal design flaw that mostly shows up decades after you've already had children is nearly invisible to natural selection. It doesn't get selected against because it isn't stopping anyone from passing on their genes. It's the same blind spot behind a lot of so-called design flaws in the human body. Evolution isn't an engineer chasing perfection. It's closer to a contractor who stops renovating the moment the building is functional enough to pass the one inspection that actually counts. And it's not just about timing. There's a genuine structural trade-off buried in here too. For a long time, the leading explanation for human childbirth being so difficult was that the female pelvis had to stay narrow for efficient upright walking, directly competing against the width needed to deliver a large-brained baby. That's a trade-off that would put real pressure on pelvis and spine shape simultaneously. Except more recent research has actually challenged that entire idea. A widely cited alternative hypothesis argues that childbirth timing may have much more to do with a mother's metabolic limits during pregnancy than with pelvis width at all, and that there's surprisingly little hard evidence tying a wider pelvis to any real cost in walking efficiency. So even the classic explanation for why the pelvis, and by extension the spine, can't just get wider and more stable, turns out to be a live, contested argument in its own right. This entire field seems to specialize in confidently taught explanations that don't hold up as well as advertised once someone actually goes looking for the evidence. Evolution took a structure built over hundreds of millions of years for walking on four legs, stood it straight up on two, and has been quietly patching the gaps ever since, one curve, one vertebra, one generation at a time. It never needed to finish the job. It only needed you to survive long enough to pass the blueprint along, which means somewhere down the line, someone's spine is going to be a little more finished than yours is, but it just isn't going to be you. Evolution doesn't build perfect bodies. It builds bodies that work just well enough to survive, reproduce, and pass their genes on. Everything else is a compromise. And once you start looking at the human body through that lens, a lot of its so-called flaws suddenly make perfect sense. Thanks for watching. If you enjoyed this compilation video, don't forget to subscribe for more videos exploring the strange story of what it means to be human.